Hello, good morning to everyone. As the president of the Italian Association for Artificial Intelligence, it is a great pleasure for me to introduce our second seminar in this spring series. And the seminar will be held by Michela Milano. So every one of us knows very well Michela Milano. So let me introduce just with a brief notes about her. So Michela is full professor of artificial intelligence at University of Bologna, and she chairs the Interdepartmental Institute of Human-Centered Artificial Intelligence, which counts about 27 departments and more than 400 researchers. She is past deputy president of the European Association of Artificial Intelligence and past executive counselor of the Association for the Advancement of Artificial Intelligence. She was also past member of the executive committee of the Association for Constraint Programming and of the Italian Association of Artificial Intelligence. A research activity concerns artificial intelligence with focus on decision support system and the optimization system. In this field, she has written more than 170 papers and peer-reviewed international conferences and journals. Moreover, she coordinated many European scientific and industrial projects. And today, Michela Milano will talk about integrating learning, optimization, and reasoning. So, Michela, thank you very much for being here, and please.
Thank you for the invitation. Thank you for really, it's a pleasure for doing this seminar. So I'm at home because, my whole region is basically under severe flooding. So the university is closed, schools are closed. So, we are in a bad situation, but I hope that you can, that my network is stable and you can manage to see the slides in a good way. Okay, so this is a topic that is very that we have investigated for the last I think 15 years. We have a surge in learning techniques, in deep learning in the last years, and basically all of us that were working on decision support system, optimization systems, can see a challenge, and in particular I think opportunities for exploiting these techniques for improving optimization and reasoning, and also on the other way around. In fact, my talk will be organized along two streams. One is how to inject machine learning models into knowledge-based systems. So systems where that are in general used for decision support and optimization. They have a strong combinatorial structure, and the models are composed by variables that are decisions that we have to take, constraints that link the possible assignment of these variables, and objective functions that define which is the best solution among the ones that are feasible. And how have we always done? So basically these models have always been created by interacting with domain experts, where they, in a way, tell us which is the problem that they want to solve, the structure, and possibly some constraints. And then we design a model, and then we propose some solution to the expert that says, oh, no, this solution is not good, or yes, we need an additional constraint, or the objective function is wrong. And in a way, this is an iterative process, a very long process sometimes. And also there is another problem that, in these cases, the accuracy of the model cannot be really measured. So we interact with experts and we encode in a given language, in optimization, in constraint programming, in mixed integer linear programming, or whatever, this model, okay? But, if we have in many domains data that are available, as it is always happens and is happening more and more often, then why don't we exploit this data and at least create part of this model by using this data, right? In this case, we could have a known accuracy, at least on the test set. And in this way, we could be able to merge some data-driven component with a knowledge base coming from systems coming from experts. So this is quite, it's called, the main method that we have used is called empirical model learning, and it's something that we have worked on for kind of 12, 13 years. So you might have seen other presentations about that. What is more, kind of new is the other integration, that is how to inject domain knowledge into subsymbolic machine learning models, like neural network or deep networks. So in this case, we have a deep network that are huge mathematical models, and they are hardly interpretable, because basically what we do during learning is to change the value of these billions of parameters, millions or billions of parameters. And from a human perspective, they are not very easily interpretable, even if there are some new approaches that try to go in this direction. But for some problems, as the one that I will present during the talk, sometimes we struggle in extracting with a machine learning or deep learning a relation when this relation between data is very complex. Okay. And in this case, sometimes we have that domain expert that have worked on that problem for many years know important pieces of information that would help the machine learning model itself. So the main question is why we should ask machine learning to learn something that we already know. Okay, so we have tried to inject knowledge into neural network and deep network, either acting on the data set, like through data augmentation or feature addition. I will tell you something in the second part of this talk, or acting on the structure of the deep network, or on regularization techniques. Okay, so I will do these two presentations. So injecting machine learning in knowledge-based system is the first part, and maybe the more mature one. So which are the problems in which these techniques are applicable? Well, first of all, we need to have problems that have a strong combinatorial structure, and where part of the problem is not really easily described through either a closed form or in a declarative way. And in general, these parts that are not so clearly modeled can be extracted through heuristics, for example. You have also the fact that decisions can influence predictions. So sometimes we are also in presence of uncertainty, but also we have the decision influence predictions and vice versa. But in particular, we need to have access to problem data, like historical data, or data that we can extract from a simulator, or even data that we can extract from the real system through sensors to create kind of training sets. So along the two directions, I will use two examples. One is what is called thermal aware workload dispatching, and it's a problem that we can find when we dispatch and allocate and schedule application on top of what is called many core systems or multi-core systems. In this case, we have this Intel SCC that was a cloud computer, single chip cloud computer with 48 cores, basically. And what we have to do is that we want to allocate programs, okay, applications on top of that. But the problem is that this very packed chip runs the risk of being overheated, right? And overheating is really bad because you don't want to damage the chip. Performances are reduced in case, for example, you have thermal control on this chip, and also you reduce the lifetime of the chip itself. So the thing that in general is done traditionally is to slow down the chip when the temperature goes high. But this, of course, results in poor performances. There are also, instead, what we want to do, these proactive techniques that you want to make a workload of your application, a dispatching, a frequency control, but based on the real temperature of this platform, right? So you need to have a thermal model. And indeed, this thermal model can be extracted by a number of things like the room temperature, I mean, if it is hot or cold, the workload on each of the 48 cores that influences the thermal model of the overall platform, the fabric of the chip, the position of the cores and the heat sinks, the transfer of heat between cores, and also the presence or not on thermal controllers that possibly slow down the chip activities if it is overheated. Now, there are indeed thermal simulators, so thermal models, of course, that are perfectly able to accurately predict the temperature in each core, given all the previously mentioned information, right? The room temperature and so on. But the problem is that every run of these simulators takes tens of seconds, okay? And if you want to insert in a combinatorial model one simulator that takes tens of seconds to evaluate each possible exponentially large number of possible assignments, that it takes forever, right? So the thing that we do is that we want to use machine learning, to learn an approximation of this thermal behavior on the basis of previous runs of code on that platform. And then we can be able to produce a training set. On top of this training set, we create a machine learning model like matching between our decisions that are how to allocate tasks on different cores, on memory and so on, and the temperature after a given delta t of time that we want to predict in a way, right? So for each core, we create a very small machine learning model that is a very simple, shallow neural network that takes as input the temperature of the room, for example, and a proxy of the workload of each core, of the core number 3, for example, and also the neighboring core, because as we said, we have a transfer of heat on core 3 starting from other cores, okay? So if we are able to train this neural network by providing previous runs that we have tried to extract from the real system, or runs that we have extracted from a simulator of this platform, then we can train this little machine learning model to, in a way, to forecast the temperature after a given time. So what can we do with this machine learning model? Well, first of all, we can have a kind of a generate and test approach. Okay, you have a combinatorial optimization component that tells you, even optimally, how to allocate tasks on each core, how to allocate memory on each core memory, and so on, and also the scheduling of these activities. And then when we have a solution that is completely unaware, agnostic with respect to the thermal dimension, we pass this solution to a black box solution evaluation that is, for example, a simulator, like in this case, and then it receives back an evaluation saying, well, this solution is completely infeasible because our chip would be burned, or otherwise, oh yes, the solution is feasible because the temperature runs smoothly. So this part here can be very expensive, because if we want to, ping pong to generate a solution and then test it, and then many of them can be infeasible, then this interaction may run forever, right? So one thing that has been proposed, quite a long time ago by Laguna, is to insert a predictor of the simulator outcome, like that can be a neural network, for example, and basically this predictor can tell us if the solution, for example, to discard, to avoid the simulation of trivially infeasible solutions, for example. So you remove part of the problem. But anyway, you can also use something which is faster than a simulator. like a set of neural networks that provide a solution very, very quickly, but still, you know, it is a generate and test mechanism. You try with a solution, you define, you evaluate the solution, and then you have a yes/no answer. Very similar to what is done, for example, in logic-based Bender decomposition. But the fact is that the evaluation does not provide cutting planes, for example, or you have to define some cutting planes that remove the solution that has been defined by the combinatorial optimization component. So if we want to avoid this generate and test mechanism, then we have to resort to what is called empirical model learning. So we want to embed this machine learning model into an optimization component. In general, it is a constraint, okay? For example, in constraint programming, it is a global constraint. And then you use this model not just to check if a solution is good or bad, but to actively reduce the search space during the execution of your, during the search of your solution, okay? So you can, for example, have this machine learning model embedded into constraints. You can have this machine learning model embedded into objective functions. So you can have a flexibility that is provided by combinatorial optimization solvers in a way, okay? In particular, we have used a lot constraint programming that is very, very flexible. So this is basically an approach that has been published already 6 years ago, and we are going on to develop and further improve this method with new machine learning models and new optimization techniques. So one thing that I would like to underline is that while traditional approaches in the inference phase are used forward, so after the training of the machine learning model, where we have, defined the model, where we have set all the parameters, and we are happy with that, then when we use the machine learning model, in general, it's used forward, right? So it's used by providing like a workload dispatching in our case, and machine learning model outputs the core temperatures for each core of our platform. Okay, so this is a forward way. So as soon as you embed a machine learning model into an optimization component, and you really embed it into, a constraint, for example, you obtain the propagation back. So it works back and forward, and this is the real strength of this approach, because in a way you can limit. So when you limit the core temperature, then you can use the machine learning model to remove those workload dispatching that would lead to a temperature that is, for example, too high. So the machine learning model becomes a constraint, and it works either on one way with the traditional machine learning way that goes forward and backward. So this is the real thing. So let's see an example. Of course, we have used many different machine learning models. We have tried to embed in combinatorial optimization models, neural networks, decision trees, random forest. In this case, I will give you just 2 examples. But also not only in one optimization techniques, but we have done a mix of machine learning with constraint programming in the talk, but also mixed integer nonlinear programming, integer linear programming, SAC modulo theory. So we have many optimization techniques that we have tried to use. So in constraint programming, for example, we have crafted inside a constraint, the neuron constraint, we have crafted basically a single neuron that takes the input as a vector of input variable, one output variable, the weights that have been trained beforehand. So the training should be done before the machine learning model is inserted into a combinatorial optimization model and the bias. And then we can also obtain, an artificial neural network constraint that takes into account more than one neuron. But basically here we have, the filtering that is performed backward and forward, and that, that propagates on the activation, from the activation function to the output, and from the output to the activation function. And then, of course, the activation function is just a weighted sum of the inputs. So we can really propagate from the input to the output and vice versa. So this is how to insert a neuron constraint in that. So let's see how it works at search time. So because as I told you, while in general for the generate and test method, you have a full solution and then you evaluate the temperature on the cores provided by a full dispatching and scheduling solution. In this case, you can use this machine learning model working at search time, trying to remove a combination of assignments that are already infeasible. Let me see an example. So we have these tasks here on the left that need to be allocated on the cores here, the cores, and then you extract some feature from this core. In particular, this ACPI is the average clock per instruction, that is a proxy of the workload that we have on a given core, okay? So here you have we have 4 cores, and therefore we have 4 neural networks, very, very small, that can produce in a way, and they can forecast which is the temperature on that core, given the temperature, the workload on each neighboring core, and of course the core itself and the room temperature. Okay, so this is something that is computed during search every time you create you make also a selection in the search tree. For example, suppose that we have already placed these 3 tasks. I mean, the red means that they are very computational intensive, so they can produce hotspots, and then we have the blue one on the other opposite that are, for example, memory bound tasks that are not requiring so much computation, and therefore as soon as you allocate, you extract these features, and then you compute, you update these temperature of your core. So for example, core 1 will be the most cooler, while the other 3 will be more or less with the same temperature, being the one that is more loaded, the hottest one, okay? So then what happens if you want to limit the maximum temperature that can be achieved on each core, like not in a controller way, I mean, controllers are doing that, but they are doing this control at runtime. So when the tasks are running, we are doing that beforehand. So by trying to foresee what will be the temperature if I do a specific assignment of tasks to core, okay? So suppose that we have an upper bound on the maximum temperature that we want to achieve on each core, just to avoid overheating. Then the nice thing of this neural network inserted into the optimization model is that they propagate back to the possible choices of tasks that they can allocate on core 2. If I have already allocated the orange one, that is, I mean, already quite hot, then I cannot assign on the same core this red one, because otherwise I would overheat. And I would violate this constraint, this threshold constraint on the temperature. So yeah, the CP model for doing that is very simple. We have, the core of task where I allocate task I is I mean, ranges on the number is a domain variable that ranges on the possible number of tasks, of cores, and then you can have some load balancing constraint, for example, that are the only one that an expert can impose if they want to obtain I mean, a reasonable temperature, but we will see in the result that they do not work very well. We can extract these feature computations starting from the allocation of the tasks to the cores, and then we have these neural network constraints for every core that basically does these tasks that we have seen I mean, before. Okay, so the propagation during search, and then you want to minimize, for example, the maximum temperature of the core, or you can choose other objective functions, like you want to minimize the average temperature. In this case, you minimize the heat spot, I mean, the heat peaks in a way. And this is the paper where we have described this kind of solution. We have also used decision trees that can be casted into an optimization model. Well, this is a little bit easier because decision trees are symbolic models, so they are fully understandable from a human perspective, and they can be seen in a way as a conjunction or disjunction of tests on features, and then you have, as a consequence, you have a class. Okay, so you can really encode already these decision trees as they are in a constraint programming model, or you can use similar tools as table constraints. You can use other encodings. We have done a number of encodings in this case. For example, we have also used a random forest for doing the same, obtaining another machine learning model into an optimization one. And we have a technical report that basically describes how to use many encodings like MDDs, compressed tuples, so decomposition approaches. So we have many other approaches, many encodings of decision trees to be embedded in a constraint. But basically, the way they propagate and they behave is exactly the same as I said for the neural networks. So just as an example, so just as a conclusion for this first part, so I have here two examples. I have here 20 instances of dispatching on the chip, on the thermal aware workload dispatching. And these first 20 here on the left, here you see this is the number 19, this is a number 0, have been generated through mixed integer linear programming, but using for the temperature a heuristic defined by human experts, okay, that in general try to provide rules like load balancing, try to push a little bit more of workload near the cooling part of the core, and so on. So as you can see, while in some solutions, I mean, it's quite reasonable, in many other, in particular, we have 1, 2, 3, 4, 5, 6, 7, where we really have a hotspot. That are these super red zones, meaning that the cores that were allocated in these zones were really with a temperature very high. On this side, instead, we have used, so this is the dispatching and of thermal aware workload dispatching using empirical model learning, and in particular these neural networks that have been trained on the basis of real data. And then we have inserted this neural network in the optimization model. And as you see, basically the really hard hotspot that we find in some instances here have disappeared. In particular, I mean, we have very good improvement, like in instance 14, where here is almost all green. The instance 11 that were severely hot, here in this case is almost all green. And also in instance 15 and this one. So we have many good, we have obtained very good results. So in a nutshell, you can use a combinatorial optimization model as every other combinatorial optimization model, as we have done for years, for decades, but then to try to, embed part of this model as a machine learning model in form, for example, of a global constraint, and also it's just a constraint. So you can add around this model many other constraints that, and the more constraints you add, basically, the more you help the propagation, and of course, it works definitely better. So we have done many extensions on this empirical model learning approach. We have a hierarchical optimization where you have the higher level of the hierarchy learn through an empirical model the behavior of the lower level of the hierarchy, and you're learning the behavior of an optimization solver. And then cast it into the higher level one. Or we have also faced offline-online optimization with that, where the offline solver tries to learn the behavior of the online one to be able to, optimize the choices so that the online one, that is the faster, the real-time one, does not take stupid decisions, but takes decisions that are in line with the overall goal. We have considered many applications, mostly by the Unibo group, but not only. So we have used, thermal control, that the one that I have just seen now, on trans-precision computing, that also the example that I will see later for explaining another example, hardware dimensioning, epidemiological model, and also from other groups, verification and adversarial examples. So we have many applications of this, and we have some material on this GitHub site, that is emlopt.github.io, which is basically contains papers, resources, running survey, some libraries that can be used freely for developing and extending the method, and also, of course, a tutorial with an hands-on example. So now, going on the other way around, so how to inject knowledge from into sub-symbolic machine learning model. So this is the slide that I have presented before, all right? So in some cases, the one that I will show you in a minute is one, we hardly obtain an accurate machine learning model in some cases when the problem is really difficult, and we can help the machine learning model in improving its performances by injecting some form of knowledge. So what we are talking about is, the example, the motivating example that I will give you here is called trans-precision computing, and comes from a project that is called OpreComp. It was a FET proactive project that is finished, but it was really interesting. So we are in the field of energy saving computing. So how to save energy, how to improve the carbon footprint of computing. And one possibility is to go toward what is called approximate computing, right? So the idea is that I can trade off the accuracy with the energy efficiency, and then I can lower the accuracy of the variables, so lower the number of bits to represent the variables of our programs, so that to save energy. Now, trans-precision computing goes one step further, because just as an example, if I have that 20% of the of the pixel of my image are corrupted or are even white, you don't really see that, right? So there are some applications where it does not really mean that you really feel a loss of performance. So trans-precision computing is something that is a little bit more advanced. So instead of deciding that all floating points should be represented with 16 bits, for example, or every floating point in my program, the trans-precision computing goes at a finer grain and wants to tune the precision of each variable in your program to the best possible allocation of bits, so that you can save energy, but also you can have a bounded computational error. Okay, so you can accept some error, provided that you're doing the trade-off between the energy and the error that you obtain. And therefore, this problem can be framed as an optimization problem, right? Because we want to decide the number of bits of each variable. So we can solve it through a mathematical model. The number of bits of each variable such that the total error achieved by the application, so the program running, is below, 20%, 10%, 5%, whatever you like, okay? So what do you have to do is that you can use data coming from many runs of your program, where variables are set at different number of bits, and through these several runs, you obtain a training set, right? That connects the number of bits that you associate with each variable of your program and the total error that you have on your application, the final error. So it cannot really be expressed through analytical formulas, except for trivial cases. And of course, there is also a research community that is trying to provide all these analytical forms that describe the error given the accuracy, the precision on the incoming variables, but they can only tackle very tiny programs, okay? So let's consider the problem definition. We have n variables, and we have to assign to each variable a number of bits, and different configuration lead to different errors, okay? So you do multiple runs on your program, and you obtain a distribution of error, okay, associated with each configuration rather than a single value. And then you want to learn the relation between precision and accuracy. The problem is that this relation is non-monotonic and non-linear, so at least in the data set that we have seen. What does it mean, non-monotonic? It means that one is supposed that if we increase the accuracy of all variables in a program, or even one variable in a program, then the error decreases. This is not always the case in the data set that we have, but of course, maybe the data that we had available were not so big. So maybe increasing the number of data can basically make those non-monotonic behavior as an outlier, okay? And so it's really a hard learning task. So we have tried with classical machine learning approach, with deep neural network, but basically the accuracy of the machine learning model was really low. So then we have tried to consider one thing, right? We know something about this problem. So why don't we try to communicate what we know about this problem to experts, right? And we can do that we have done this through 3 different approaches. We have added features to the data set. We have used ad hoc network topology, so the neural network topology, and we have used the regularization function and data augmentation. But first of all, let me try to say what we know about this problem, okay? So first of all, when we have variables in a program, they are related in terms of precision. Why? Because, for example, they appear in the same expression. So if they appear in the same expression, every compiler makes, a cast in the highest possible type, and then performs the operation, right? The set of operations in the expression. So in this way, having a variable with a lower number of bits is completely useless, right? And you have the graph of dependencies because you know perfectly which variable appears in each expression, because you see the program, right? So you have this graph of dependency. One thing that you know, that we know. Second thing, the monotonicity. So indeed, we can expect that this problem is monotonic, right? Because basically, if you have a set of bits that are not needed to be powers of 2, of course. We have 11 bit for the first, 8 bit for the second, 21 for the third, and 11 for the fourth. And then you have this other configuration, 20, which is larger than 11, 17 that is larger than 8, 34 that is larger than 21, and 11 that is equal. Then we can say that CJ is dominant with respect to CI, CCI, right? So basically, we consider in general that the error of CJ is lower than the error on CI, or the accuracy is higher, right? So we want to enforce this monotonicity during the learning process, even if there are some observations in the training set that do not confirm this behavior. But we want to consider these as outliers. So we have these 3 methods, right? So just to go back: feature addition, ad hoc network topology, and regularization. These are 3 methods that we want to use to communicate to the neural network the knowledge that we already know, okay? So we have tried to use a feature addition. So in particular, if we have that, we have an assignment, right? We want to we have an assignment x4 equal to x1, then we want to grant a larger number of bits to x4 with respect to x1, because or an accumulator, for example. You want, if you have an accumulator and variable that are accumulated there, then the accumulator should have a larger number of bits with respect to the variables that are summed there, for example, or multiplied there. So we add features that represent in the data set, that you can compute completely having the data set and values, that is the difference between these two variables. And each feature corresponds to a logic binary constraint that can be used to express this domain knowledge. The second way to inject this knowledge is the ad hoc network topology. Since we have the dependency graph, we have tried with the graph convolutional layers. Okay, so we have 2 adjacency matrix, so the feature matrix and the adjacency matrix. We have used these graph convolutional neural networks, but we will see that this experiment, at least for this problem, didn't give so many interesting results. And then we have this regularization. So in particular, we add a penalty term to our mean square error, where basically we assume that xj is dominant with respect to xi, and we use a weight for this regularization term. So we have 2 approaches, regularization and data augmentation, because we can create additional configuration in the training set, that are synthetic in a way, that have higher or lower level of precisions. And we have done this data augmentation. So in general, in the experimental evaluation, we have selected, different models, different data-driven models to obtain a baseline, and then we have tried to see, basically, to inject this knowledge into these neural networks and try to evaluate the mean absolute error that they were producing. And also we measured the number of violated constraints, that is another important issue. So these are some results. We have this baseline that is the the base and the neural network without any knowledge inserted. And then the regularization did not approve very much accuracy. I mean, yes, a little bit, but not much. Especially with small data sets, it had a reduction of violated constraints, while the additional features here, this one, produced a reduction in the prediction error of almost 40% on average. So while indeed instead the GCNN approach, so meaning using networks that have a structure of these graphs, did not improve the accuracy at all. I mean, it was worse in many cases. So we have done also other works of our research group, and basically we have tried many other ways of mixing in machine learning with optimization and reasoning. In particular, we have this moving target. That is a AAAI paper that was of 2 years ago. That is another way to inject constraints into neural network and deep networks. We are now currently working on integrating reinforcement learning in combinatorial optimization, and in particular also in online offline optimization. This is a paper that is now on core, but it's submitted. So we are working a lot on this research subject, and we are always looking for people and PhD and researcher people that want to collaborate with us. So in conclusion, I mean, there are many more approaches from the literature. I really don't want to try. I didn't do a survey because it would take forever, but I mean, they are all trying to combine the advantages of data-driven and knowledge-based approach, because we still have data. Yes, we have machine learning that is very good, but we cannot miss the super important and precious experience of human experts. So this is a way to combine the two worlds. And also there are some links with trustworthy AI dimensions, because, for example, imposing constraint in a neural network can help, for example, achieving fairness in neural network. And we are also, exploring a lot as a group this kind of topics, because we think that we can easily enforce this fairness constraint, this ethical constraint in a deep network or a neural network that are hardly controllable otherwise. So I think that's all.
Thank you very much. Thank you very much, Michela. Yeah, thank you very much for this nice presentation. And so I would like to start the discussion. So, Giuseppe.
Yes. So, thank you for your talk. Very nice. I wonder what the success of generative AI, okay, how this success is impacting this kind of research. So,
yeah, that's definitely.
Let me comment a little bit more. So,
yeah, sure.
We recently had a discussion with Tim Taylor on Transport AI, and somehow we thought that this think of ChatGPT and generative AI is changing a little bit the scene, and that we should in fact address this change as expert in Transport AI. So maybe you can comment a little bit on this.
Yes, I mean, yeah, of course. I mean, the ChatGPT is a little bit. I mean, at least as far as I know, not really at the point that it can solve problems and has reasoning capabilities that are at this point. But generative AI is really interesting for me, because I think that we can really work on the data side in a way that is extremely interesting. So let me say a little bit more about that. So suppose that you want to measure like how trustworthy is a system, or even how you can transfer learning from one machine to another, right? So you have two identical machines. The model that you have for one never work on the second one. So, how can we use this generative AI for creating data sets that are similar to the first one, but not exactly identical? And if you can measure, for example, the distance between these two data sets, then you can, in a way, create control experimentation environment where you can, for example, test how long, for how long your machine learning model is still fair, even if you stress it. Or, for example, how can you create data sets that are different, more different, and then at some point the transfer learning does not work at all. Or, for example, at the beginning where they were kind of similar, it works. So I think that the generative AI is very, very good for us for creating how can I say, controlled experimentation environment that can enable us to measure, for example, how the performances of our machine learning models and even the optimization models. This is one direction, of course. There are many other possibly.
Thank you, Michela. There are some questions in the chat, so let's start with a question by Carlo Adornetto, who is asking, can injecting knowledge bring any advantage in terms of networks explainability?
Yes, this is a very, very good question. Indeed, in a way, you know which is the knowledge that you have injected, and the fact that you can test whether your network has, for example, satisfied some constraints. So it's a kind of a posteriori checking, and this can enable a little bit of explainability, but cannot be seen really in the. At least we have not investigated, the traditional explainability way, like why a network has provided a given result. Of course, we can say that a network satisfies some constraints that are given by the human expert, or we can say that a network satisfies some constraint in the 90% of the cases. So we have these statistics that can be used, and they can be also improved through enforcing this constraint in the network. Because even if you enforce constraint, they are not satisfied at 100% in the neural network. But you increase a lot the number of cases in which the network provides a feasible solution.
Thank you, Michela. So another question by Andrea Micheli. Would it make sense to use logic tensor networks for injecting the symbolic constraints you mentioned in the network?
It's possible, definitely, Andrea. Let's work on it. Let's work together on it. This is a very good point.
Okay. So let's see whether there are other questions. In the meanwhile, I have a question. So I was really interested by the second part of your talk. I have a question related to how we can generalize your approach to other scenarios. So what about doing some general approaches to data augmentation and or constraining the loss functions?
Yes. That's a kind of a preliminary we have a set of preliminary results. Okay, so the step toward generalization is something that we are trying to do. So we are trying to understand, analyzing several applications, whether there is a common behavior, like injecting. For example, it's not always the case that using a graph neural network that follows the structure of your constraint graph, because that would be very, very easy to do, right? So, a constraint graph can be always extracted, or hypergraph can always be extracted by a combinatorial optimization problem. So if we can use a graph neural network for taking into account a constraint in the form of constraint hypergraph, that would be extremely general. We are not yet there, absolutely. So, but yes, we are trying to find at least some guidelines to achieve good behavior. I mean, even for other for general problems, for general combinatorial optimization problems. My suspect is that when we use constraints in the form of in the form of graph, so it's very, very difficult to achieve a general how can I say, general results, because when you have hypergraphs is even worse. And in general, I mean, for real problems, we always have hypergraph because you have n-ary constraints, like global constraints. But maybe for mixed integer linear programming is a little bit simpler. But I don't know. I don't really know. So we are working on this.
Okay.
I hope to have an answer in few months.
Thank you, Michela. So there is another question by Aldo Riccioppo. Prior knowledge does result in more lightweight models and optimization. Did you investigate also this aspect?
You mean, sorry, but you mean lightweight models, machine learning models, or optimization models?
I guess neural networks. So does this prior knowledge has an impact on the size? So maybe this is also related to the topic of green AI in general.
No, I don't think so. No, I don't think so. But this is maybe something interesting to elaborate. No, we have not seen this aspect. I'm sorry about that, but no, we have not considered that. That's a good idea anyway. Maybe we could.
Maybe saving computational resources by the knowledge that you inject into the network. That can be a good idea. So, are there further questions? Otherwise, I think that we can really thank Michela. Michela, so it was a great pleasure for us having you here as a guest speaker, as a keynote speaker. And so, thank you.
Thank you.
And so we will conclude this spring seminar with the next month with the last seminar, which will be held by Niccolò Cesa Bianchi. So, bye.
Ciao, thank you. Bye-bye.